Bismillahir Rahmanir Rahim. Alhamdulillahi Rabbil Alameen. Wa sallallahu wa sallama ala Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. In the last two presentations, I have explained why the claim that the universe began to exist is evidence for the existence of God. I have explained that there are two kinds of evidence for the fact that the universe began to exist: scientific evidence and philosophical evidence. I explained the scientific evidence in the sixth presentation of this series, in which I showed why the fact that the universe began to exist is now considered scientific fact. And I explained some of the philosophical evidence in the next presentation, in which I showed that the claim that the universe began to exist is straightforward, intuitive, and a simple generalization of our everyday experience, whereas the claim that the universe did not begin to exist is strange, counterintuitive, and contrary to our everyday experience. I then went further to show you three rational arguments that conclusively demonstrate the falsehood of this second claim, explaining that it is logically equivalent to two other claims, and that carefully reflecting on the meanings and implications of each of these claims demonstrates conclusively that they are all false, and that the universe therefore did in fact begin to exist. I then concluded the previous presentation by hinting at a modern objection to these arguments. This objection claims that modern mathematics has shown that infinities can in fact exist, and that therefore it is possible for the universe not to have a beginning by existing for an infinite quantity of time. I will show in this presentation that this is an invalid objection because infinity is an imaginary concept. A more precise way of saying that infinity is an imaginary concept is to say that mathematical infinities do not describe physical quantities. Let me explain what this means with an example. If someone says that 5 years of time have elapsed, they have said something that is coherent, because time is a physical quantity and 5 is a number that has been used since the invention of numbers to describe physical quantities. As I will explain shortly, 5 is a natural number, and the natural numbers were invented to count physical things. The number of eggs in a basket, the number of trees in a field, the number of stars in the sky, and so on. The statement 100 years of time have elapsed is also a coherent statement because, like the number 5, the number 100 is also a natural number that has historically been used to describe physical quantities. The natural numbers can be extended indefinitely. They can get larger and larger. There is no largest natural number. I will explain that in greater detail shortly. That is why when we use extremely large natural numbers today, beyond the imaginations of people who lived in the pre-modern age, numbers such as 14 billion in the statement 14 billion years of time have elapsed. Remember from the sixth presentation in this series that is approximately how old scientists think the universe is. When we use extremely large natural numbers such as this, our statements remain coherent because even though they are large beyond the imaginations of people who lived in earlier times, numbers such as 14 billion are still natural numbers that can be validly used to describe physical quantities. But if we substitute the numbers 5, 100, and 14 billion with the mathematical concept of infinity, the statement is no longer a coherent statement because, as I will explain shortly, the concept of mathematical infinity is not a number that can be validly used to describe physical quantities. That is what I mean when I say that mathematical infinities do not describe physical quantities. And that is what I mean by the title of this presentation when I say that infinity is an imaginary concept. In order to understand why infinity is an imaginary concept, or in other words, why mathematical infinities do not describe physical quantities, we need to understand what a physical quantity is, what a number is, and what mathematics is all about. This will take some time, and this presentation is therefore longer than other presentations in this series on why Islam is true. But I hope that if you listen to it carefully, it will clearly show you that the modern objection that I am considering in this presentation is completely baseless. If that modern objection is not something that you are very concerned about, you can simply skip this presentation and move on to the next presentation in this series. Let's begin with physical quantities. The term physical quantity is a technical term that Muslim theologians inherited from Aristotle, who listed it as one of his famous 10 categories. In the Arabic terminology of the Muslim theologians, it is called al-kam. Although the Muslim theologians inherited the general idea of physical quantities from Aristotle, like most modern philosophers and scientists, they found that his conception was flawed. They therefore corrected his conception to bring it into agreement with the way that things really are. I will now explain the way that the Muslim theologians explained the concept physical quantity, and then use that explanation to show you why mathematical infinities are not descriptions of physical quantities, and then use that to show you why the invention of mathematical infinities is completely unrelated to whether or not the universe began to exist. A physical quantity is a mental abstraction that describes how many or how much a physical object is. For example, you can ask how many eggs there are in this carton of eggs, and the answer to your question might be, for example, 12 or a dozen eggs. The number 12 or the unit dozen describe the quantity of eggs, how many eggs there are, in other words. This kind of physical quantity is called a discrete quantity. In the Arabic terminology of the Muslim theologians, it is called al-kam al-munfasil. The second kind of physical quantity is a continuous quantity. While a discrete quantity describes how many distinct things there are in a collection of objects, like a carton of eggs, a continuous quantity describes how much one particular object is. How much paint, for example, there is in a can of paint. The can of paint might contain 5 liters of paint. 5 liters is a description of the quantity of paint in the can because it describes how much paint there is in the can. In the Arabic terminology of the Muslim theologians, a continuous quantity is called al-kam al-muttasil. The difference between discrete and continuous quantities is that discrete quantities arise from the hypothetical addition of multiple objects, whereas continuous quantities arise from the hypothetical division of a single object. The number of eggs in a carton is a discrete quantity because it arises from the addition of many distinct eggs. The amount of paint in a can is a continuous quantity because it arises from the division of a single can of paint into a number of hypothetical parts or liters. The Muslim theologians observed that the necessary characteristics of everything that is a physical quantity are that it be divisible, that it be composed of units, and that it be describable as being equal to, more than, or less than other quantities. The collection of 12 eggs that we examined is a quantity because it has all 3 of these characteristics. It is divisible. For example, you can divide the 12 eggs into 2 groups of eggs, a group of 5 and another group of 7 eggs. It is also composed of units. The 12 eggs are composed of 12 units, each unit corresponding to an individual egg. And it can be described as being equal to another collection of 12 eggs, more than a collection of 6 eggs, and less than a collection of 30 eggs. The collection of 12 eggs is therefore a physical quantity. The 5-liter can of paint that we examined is also a quantity because it too has all 3 of these distinctive marks. It is divisible. For example, you can divide it into 2 smaller cans of paint containing half its quantity. It is composed of 5 units called liters, and it can be described as being equal to a can of paint that has the same quantity of paint, more than a can of paint that has a smaller quantity, and less than a can of paint that has a larger quantity. The can of paint is therefore a physical quantity. I will now show you that the mathematical concept of infinity does not represent a physical quantity because it is not divisible, it is not composed of units, and it cannot be described as being equal to, more than, or less than another physical quantity. But before I do that, I need to give you a quick overview of the history of numbers and the history of mathematics. There are many different kinds of numbers. 0 is a number, 1 is a number, 1/2 is a number, the square root of 2 is a number, pi is a number, -3 is a number, and I, the imaginary unit of complex numbers, is also a number. Although today we consider all of these objects to be numbers, that has not always been the case. The first kinds of numbers to be invented were what we now call the natural numbers. Historically, the natural numbers began at 2 and continued on to 3, 4, 5, 6, and so on without ever reaching any upper limit. I will explain in a couple of moments that 1 and 0 were not considered natural numbers when numbers were first invented. The natural numbers were invented to count discrete quantities, how many objects there were in a given collection, 12 eggs, 6 trees, 100 stars, and so on. They are called natural numbers because they are the numbers that we naturally use to count numbers of objects. 12, 6, and 100 are natural numbers because we use them to count numbers of objects. But numbers such as the square root of 2, pi, and -3 are not natural numbers because we don't use them to count numbers of objects. You never walk into a supermarket and come out with pi apples, nor do you ever go to a car dealer to buy the square root of 2 cars, and it is impossible to buy -3 of anything because it is not possible to have less than nothing of anything. 0 is not a natural number because it is not used to count numbers of objects. If you don't have anything, then it is very unnatural to tell someone how many apples you have by saying that you have 0 apples. If you have apples, it is not the case that you don't have anything, 0 apples in other words. If you don't have anything, you don't say that you have 0 apples. Rather, you say that you don't have any apples at all. Even though mathematicians now consider 1 a natural number, historically it was not thought of as a number at all, because the first numbers, natural numbers in other words, described a quantity of things. A number of things, in other words. And if you only have one thing, you don't have a quantity of things. The number 1 does not describe any quantity. Rather, it is the unit element from which all discrete quantities are constituted. The counterparts of natural numbers, and probably the next kind of numbers to be invented, are fractions. I have shown that the natural numbers were invented to measure collections of discrete objects, or in other words, discrete quantities. Fractions, on the other hand, were invented to measure the hypothetical divisions of a single object, or in other words, continuous quantities. Consider a piece of wood that you want to saw into 2 equal parts. Before you begin, you will divide the pieces of wood in your mind and picture its 2 halves. The number 1/2 represents each of these 2 quantities that you envision in your mind before you begin sawing. These 2 quantities are the hypothetical parts of the piece of wood that you haven't yet sawed. They are hypothetical because they only exist in your mind while the original whole is still intact. After you saw the piece of wood into its 2 actual parts, the 2 actual parts become distinct and independent wholes and are not half of anything else. They are only 1/2 of the piece of wood when considered hypothetically in relation to the original whole that they came from. After they become actual, they are no longer half of anything. This is what we mean when we say that a continuous quantity is the hypothetical part of a single object. Fractions, such as 1/2, measure such continuous quantities. Other examples of fractions are 1/3, 1/4, 3/5, 7/8, and so on. Every one of these fractions measures a continuous quantity. We can combine the fractions and the natural numbers to form a collection of mixed numbers consisting of a whole or natural number part and a ratio or a fractional number part. Mathematicians call such numbers rational numbers. The word rational in the expression rational number does not mean logical or reasonable as it means in everyday speech. Rather, it means to do with ratios. rational numbers are numbers that involve ratios. The collection of rational numbers that I have just described begins at 2. In modern mathematics, however, the rational numbers also include 1, 0, and negative numbers. I have just explained that none of these were considered numbers by ancient mathematicians. For ancient mathematicians, a number was only a number if it represented physical quantities, and none of these numbers represent physical quantities. For modern mathematicians, however, numbers are different kinds of objects. Understanding the difference between what ancient mathematicians thought numbers were and what modern mathematicians think numbers are is the key to understanding why infinity is an imaginary concept, or equivalently, why mathematical infinities do not represent physical quantities. The difference between ancient and modern mathematics is that modern mathematics is more abstract than ancient mathematics. The two most important mathematical inventions that led to this greater level of abstraction were algebra and the Cartesian plane. I will now show you what each of these are, why they increase the level of mathematical abstraction, and why they naturally lead to a change in the concept of number. Let's start with algebra. I have just explained that for ancient mathematicians, numbers represented physical quantities. Another way of saying this is that numbers were an abstract and general way of analyzing quantities or collections of objects. Consider this quantity or collection of apples, this quantity or collection of eggs, and this quantity or collection of trees. If you look at these collections at a low level, they are all different from each other because they are all collections of different kinds of objects. The first is a collection of apples, the second a collection of eggs, and the third a collection of trees. But if you step back and look at them in a more general way by abstracting away the particular objects that they are composed of, and think of them simply as quantities of some object, any object at all, then they are the same. When these collections are considered in this abstract way, each one of them has the same quantity of objects. In this example, we express this identity of abstract quantity with the number 5. Other numbers, 6, 7, 8, and so on, similarly represent other abstract quantities. This is what I mean when I say that for ancient mathematicians, numbers were an abstract and general way of analyzing quantities of objects. With the invention of algebra, mathematics became more abstract. Instead of abstracting physical quantities, algebra abstracted the numbers that represented those physical quantities. For example, in the algebraic equation x plus y equals 100, the symbols x and y are abstractions of numbers because they represent any pair of numbers that add up to 100. They can represent 2 and 98, 3 and 97, 4 and 96, and so on. X and y are not numbers, they are abstractions of numbers. Algebra was invented to solve real problems. This equation, for example, might have been written to represent a scenario where a shepherd keeps 100 sheep in 2 pens. X represents the number of sheep in one pen, y represents the number of sheep in the other pen. The number of sheep in both pens must always add up to 100. If the shepherd counts 10 sheep in the first pen, then he knows that there must be 90 in the other pen, because 10 plus 90 equals 100. If he counts 25 sheep in the first pen, then he knows that there must be 75 in the other pen, because 25 plus 75 equals 100, and so on. Now, consider a scenario where he counts 99 sheep in the first pen. How many sheep are there in the second pen? If the purpose of numbers is merely to count quantities of objects, then this is an invalid question, because the second pen does not contain any quantity of sheep. It only contains 1 sheep, and 1 sheep is not a quantity. It cannot be an answer to the question how many, because how many can only be answered by a quantity, and to be a quantity, there must be more than one of a thing. But if the purpose of numbers is to represent valid solutions to an algebraic problem such as this one, then our concept of numbers needs to be extended to include the number 1, because the number 1 is a valid solution to this scenario. Now consider a scenario where he counts 100 sheep in the first pen. There are now no sheep in the second pen. If the purpose of numbers is merely to count quantities of objects, then to ask how many sheep are there in the second pen is an invalid question, because nothing is not a quantity. But if the purpose of numbers is to represent valid solutions to an algebraic problem such as this one, then our concept of numbers needs to be extended even further to include the number 0, because the number 0 is a valid solution to this scenario. Let's review what just happened. Before algebra, numbers abstracted physical quantities of real objects. After algebra, algebraic symbols such as x and y abstracted numbers. The techniques of algebra were then applied to problems such as this one, the one that I have just described. This application led to an extension of the concept of number. Numbers went from being concepts that represented physical quantities to being concepts on which certain operations, addition, subtraction, multiplication, division, and so on, could be validly performed to arrive at a valid solution to some problem to which the techniques of algebra were applied. With the invention of algebra, mathematics became more abstract, and this led to a change in the concept of number. Grasping this difference between numbers in ancient mathematics and numbers in modern mathematics is the key to grasping why infinity is an imaginary concept and why mathematical infinities do not represent physical quantities. So make sure that you understand this well. We will return to this difference again and again in the rest of this presentation. The next important mathematical invention was the Cartesian plane, named after the 17th century French philosopher and mathematician René Descartes. Descartes used his plane to visually represent algebraic equations. The Cartesian plane consists of a horizontal axis called the x-axis and a vertical axis called the y-axis. Every point on the plane can be represented with a pair of coordinates that are determined by a point on the x-axis and a point on the y-axis. Any algebraic equation with an x value and a y value, such as the equation that we have just been studying, x plus y equals 100, can be visually represented on this plane like this. When x is 3, y is 97, and x plus y equals 100. When x is 50, y is also 50, and x plus y equals 100. When x is 70, y is 30, and x plus y equals 100, and so on. But I want you to note two things about this visual representation. First, note that the line that represents the equation extends to the left into the negative values of x, and it also extends into the right into the negative values of y. These are not valid scenarios in the real-world problem that the equation was written to solve. It is impossible for the shepherd to walk into any of his two pens and find that they contain less than 0 sheep. Extending the ancient natural numbers to include 1 and 0 makes sense in this case, but extending them to include negative numbers does not. The second thing that I want you to note is that the line is continuous, not discrete. That means that it doesn't just consist of whole number values of x and y, but also rational number values of x and y. When x is 12.5, y is 87.5, and x plus y equals 100. This is a valid solution to the algebraic equation, but it is not a very likely scenario in the real-world problem that the equation was written to solve. The shepherd will never walk into the first pen to find 12.5 sheep in it. If he did, he wouldn't worry about how many sheep there might be in the second pen. He would worry about the wolf that came and ate half of one of his sheep and wonder how many sheep the wolf might have eaten in the other pen. I have just illustrated how algebra and the Cartesian plane transformed mathematics. Ancient mathematics was closely tied to counting numbers of objects in the real world. Modern mathematics is more abstract. It steps away from objects in the real world and turns numbers into abstract mathematical objects of mathematical operations. The numbers or the symbols x and y represent any abstract object that can be added, subtracted, multiplied, divided, exponentiated, or rooted. The resulting abstract mathematical objects can then be represented on the Cartesian plane, regardless of whether or not the values that they represent have any meaning in the real world. Modern mathematics generalizes these abstract mathematical objects so that algebraic equations have as wide a range of solutions as possible, all subject to a number of carefully defined mathematical rules. A modern mathematician is someone who studies different kinds of mathematical objects, different kinds of mathematical operations on those mathematical objects, and different kinds of mathematical rules that the objects and operations must conform to. All of these form different kinds of mathematical systems, and the mathematician then examines the behavior of these mathematical systems and the kinds of solutions that they generate. This study is highly abstract and completely separated from the real world. Ancient mathematics had a direct meaning in the real world. This is no longer the case with modern mathematics. All that matters in modern mathematics is the abstract internal coherence of mathematical systems. What used to be numbers for ancient mathematicians are mathematical objects for modern mathematicians. The mark of a valid mathematical object is not whether it represents a quantity of real-world objects, but whether it coherently fits into a mathematical system of objects, operations, and rules. For the sake of clarity, I will now stop referring to things like 0, 1, 1/2, the square root of 2, pi, -3, and I as numbers. Instead, I will call them mathematical objects. The term mathematical object, by the way, is not a term that I have invented in this presentation. It is a well-established technical term in the philosophy of mathematics, and it is, in fact, what a real mathematician would call all of these things. In order to explain as clearly as possible why infinity is an imaginary concept, or, in other words, why mathematical infinities do not represent physical quantities, I want to look briefly at the last kind of mathematical object that I have just mentioned, the imaginary unit I. Imaginary numbers come from algebraic equations such as x squared plus 1 equals 0, which have no solution on the Cartesian plane. If you represent the equation y equals x squared plus 1 on the Cartesian plane, you will see that the resulting curve or parabola never intersects the x-axis. This shows that there is no value of x for which y equals 0. X squared plus 1 never equals 0. The equation x squared plus 1 does not have any solution. You can see the fact that it does not have any solution even without the Cartesian plane. If x squared plus 1 equals 0, then x squared equals -1, and x equals the square root of -1. If you plug in -1 into your calculator and try to find its square root, you will get an invalid result. Your calculator is telling you that there is no such thing as the square root of -1, because the square root of any mathematical object b is a number a which, when multiplied by itself, gives b. If a is a positive object, then multiplying it by itself will give a positive answer. If, on the other hand, a is a negative mathematical object, then multiplying it by itself will also give a positive number. Since there is no such thing as a mathematical object that is neither positive nor negative, there are no other options to consider, and the square root of -1 does not produce any valid result. Because it is only valid to perform the mathematical operation of square root on a mathematical object that is a positive number. But in modern mathematics, whether or not a result is valid can be changed by changing the rules of the mathematical system in which the mathematical operation is taking place. The algebraic equation x squared plus 1 equals 0 does not have any valid result in the mathematical system that is represented by the Cartesian plane, but that can be changed by simply defining a new mathematical object, which, when it is squared, gives a value of -1, or for that matter, -2, -3, -4, or minus anything. That is exactly what mathematicians have done. They have defined a new kind of mathematical object called an imaginary number. They have then redefined the square root operation so that it can, in fact, be performed over a negative number, generating a new kind of mathematical object. This new kind of mathematical object is an imaginary number that is neither negative nor positive and does not exist anywhere on the Cartesian plane. Because of the invention of this new kind of mathematical object, this equation now has a valid solution. That solution is I, which is the unit of imaginary numbers, just as 1 is the unit of the natural numbers. Now, even though it is impossible for there to be a negative number of real-world objects, and even more impossible for there to be an imaginary number of real-world objects, both negative and imaginary numbers are important for modern science. In ancient times, people used mathematics to count numbers of objects. Today, our inferences about the real world are more complex than simply counting numbers of objects. The techniques of modern mathematics and its new kinds of mathematical objects and operations are now used to make inferences about the velocity of a moving object, the voltage and current of an electric circuit, the pressure oscillation of a sound wave, the rotation of planets around the sun, the location of an electron around an atomic nucleus, and even the behavior of financial markets. These scientific inferences are simply not possible without extending mathematical and objects and operations to include negative numbers and complex numbers. We need negative numbers for such inferences because whether a number is negative or positive is used to represent the direction in which an object is moving, the direction in which an electrical current is flowing, the coordinate position of a rotating planet relative to the center of an imaginary two-dimensional Cartesian plane, the coordinate position of an electron relative to the center of an imaginary three-dimensional Cartesian plane, and rising or falling prices on the financial markets. We need complex numbers for such inferences because they are indispensable to simplify the analysis of sinusoidal functions in AC electric currents and to transform sound waves into a series of sinusoids using what is called a Fourier analysis. These methods simplify the analysis of such natural phenomena and facilitate the design of complex technology that allows us to take advantage of those phenomena and subject them to our purposes. These are all good things. Modern mathematics has extended the capabilities of ancient mathematics. Instead of merely being a tool for counting sheep, mathematics is now a tool for designing airplanes, communicating instantaneously with people around the world, finding cures for previously incurable diseases, and sending satellites into space. But that is not the context in which I am examining modern mathematics in this presentation. I am examining modern mathematics to show you that it is not valid for an atheist to object to the arguments that I explained in the previous presentation by saying that the arguments for the fact that it is not possible for the universe to not have begun to exist, that it is not possible for the universe to have existed for an infinite quantity of time, that it is not possible for an infinite quantity of time to elapse. It is not valid for an atheist to object that these arguments are incorrect simply because modern mathematics includes a mathematical object called infinity. The reason why this is not valid is that while it is true that the numbers of ancient mathematics represented physical quantities, that is no longer true about the mathematical objects of modern mathematics. Let me illustrate this first with negative numbers and complex numbers, and then later with mathematical infinities. It is meaningful for a scientist to use negative numbers to represent the speed of a car moving backwards. The minus sign in this case represents direction. But it is meaningless for a shepherd to say that there are -5 sheep in his pen, or for a timekeeper to say that -5 hours have elapsed, because the number of sheep in the pen and the amount of time that has elapsed are physical quantities. And even though negative numbers are valid and useful mathematical objects for many kinds of scientific inference, they cannot represent physical quantities. They cannot answer questions like how many or how much. It is meaningful for a scientist to use complex numbers to represent the alternating electric current or voltage that comes out of a power supply, but it is meaningless for a shepherd to say that he has e to the ix sheep, or for a timekeeper to say that e to the ix hours have elapsed, because the number of sheep in the pen and the amount of time that has elapsed are physical quantities. And even though complex numbers are valid and useful mathematical objects for many kinds of scientific inference, they cannot represent physical quantities. They cannot answer questions like how many or how much. We can see more clearly why negative numbers and complex numbers do not represent physical quantities by returning to the 3 necessary characteristics of every physical quantity that I explained at the beginning of this presentation. The first necessary characteristic is that it be divisible. -6 or 6i apples, whatever that might mean, is not a physical quantity because it is not divisible in the way that 6 apples, for example, are divisible. You might object that -6 and 6i are indeed divisible. They are both, for example, divisible by 3. -6 divided by 3 equals -2, and 6i divided by 3 equals 2i. But that is not what we mean when we say that physical quantities must be divisible. What we mean when we say that physical quantities must be divisible is that they must be physically divisible into 2 smaller physical quantities, or more than 2 smaller physical quantities. 6 apples, for example, are divisible into 3 smaller physical quantities of 2 apples each. This kind of division has the same name as the mathematical operation of division that we just saw applied to negative and complex numbers, but it has a different meaning. The mathematical operation of division used to have a similar meaning when it was used for natural numbers and fractions, which described physical quantities, but when the concept of numbers was extended to include negative and complex numbers, the meaning of the mathematical operation also changed. This is an important point to remember. When the objects of mathematical operations change, the meaning of those operations also changes. The second necessary characteristic of every physical quantity is that it be composed of units. -6 or 6i apples, whatever that might mean, is not a physical quantity because it is not composed of units in the same way that 6 apples, for example, are composed of units. Again, you might object that negative numbers and imaginary numbers are both composed of units. -6 is composed of the negative unit -1, 6 of them, and 6i is composed of the imaginary unit I, 6 of them. But again, that is not what we mean when we say that physical quantities must be composed of units. What we mean when we say that all physical quantities must be composed of units is that they must be physically composed of a kind of physical thing. 6 apples, for example, are composed of the physical unit of 1 apple. Negative numbers are indeed composed of the negative unit -1, and imaginary numbers are indeed composed of the imaginary unit I, but this mathematical composition does not mean the same thing as physical composition. Mathematical composition used to have the same meaning as physical composition when we only used natural numbers and fractions, which describe physical quantities. But when the concept of numbers was extended to include negative and complex numbers, the meaning of mathematical composition also changed. As I have just explained, when the objects of mathematical operations change, the meaning of those operations also changes. The third necessary characteristic of every physical quantity is that it be describable as being equal to, more than, and less than another physical quantity. -6 and 6i apples, whatever that might mean, is not a physical quantity because it is not describable as being equal to, more than, or less than some physical quantity, in the same way that 6 apples, for example, are equal to another quantity of 6 apples, more than another quantity of 2 apples, and less than another quantity of 10 apples. Again, you might object that -6 is equal to -6, more than -10, and less than -2, and 6i is equal to 6i, more than 2i, and less than 10i. But again, that is not what we mean when we say that all physical quantities must be describable as being equal to, more than, or less than another physical quantity. What we mean when we say that physical quantities must be describable by these things is that they must be describable as being physically equal to, physically more than, and physically less than another physical quantity. Negative and imaginary numbers can indeed be operated on by the mathematical operations of equality, greater than or less than, but these mathematical operations do not mean the same thing as the physical equality, physically greater quantity, or physically smaller quantity of physical things. They used to have the same meaning when we only used natural numbers and fractions, which described physical quantities, but when the concept of numbers was extended to include negative and complex numbers, the meaning of these mathematical operations changed. To say again what I have already said twice before, when the objects of mathematical operations change, the meaning of those operations also changes. I have now shown you in great detail that negative numbers and complex numbers are mathematical objects that are part of a modern mathematical system of inference that has many useful applications, but that they are a different kind of mathematical object than ancient numbers because they do not represent physical quantities. Now that you understand what a physical quantity is, what a number is, and what mathematics is all about, you are ready to understand why infinity is an imaginary concept, or, in other words, why mathematical infinities do not describe physical quantities. There are two kinds of infinities in modern mathematics, not just one, as most people imagine. The first kind of infinity is represented by a sideways figure 8. This is the more well-known kind of infinity and is used in the calculus. The second kind of infinity is less well-known, but, as we shall see, it is more relevant to this presentation than the first one. This second kind of infinity is represented by the first letter of the Hebrew alphabet, the Aleph, and is used in set theory. Let's look at each one in turn. The first kind of infinity, the sideways figure 8, appears in mathematical statements like this one. We read this statement by saying that the limit of 1 over x as x approaches infinity is 0. To see what this means, let's draw y equals 1 over x on the Cartesian plane. It looks like this. When x is 1, then y, or 1 over x, is 1. When x is 2, then y, or 1 over x, is 0.5. When x is 4, then y, or 1 over x, is 0.25, and so on. As x gets bigger and bigger, 1 over x gets closer and closer to 0. The larger x is, the closer 1 over x is to 0, and this is true without any limit. A modern mathematician would say that this limit statement means that 1 over x can be made as close to 0 as we like by making x sufficiently large. The infinity symbol in this statement, therefore, does not refer to any quantity of anything. It is not even a point on the x-axis. No matter how far you go on the x-axis, you will never reach a mathematical object called infinity. The infinity symbol, along with the arrow in this statement, simply describes the fact that x can always be made larger and larger. This is, in fact, true of every physical quantity. Every physical quantity can be made larger and larger. This follows from the three necessary characteristics of every physical quantity. If every physical quantity is composed of units, then you can always make it larger by adding another unit to it. Every physical quantity can always be made larger and larger. Recall from the previous presentation that this property of physical quantities, the fact that they can always be made larger, is one of the arguments for the fact that it is impossible for the universe to have existed for an infinite quantity of time. An infinite quantity of time is one that does not have an end or limit, but you can add 1 to something only if it has a limit. Since you can always add 1 to the quantity of time that has elapsed, it must have a limit. This was a quick explanation. For a fuller explanation, please watch the previous presentation. The infinity symbol in this statement is therefore describing a state of affairs that is an argument for the fact that it is impossible for an infinite quantity of time to elapse, and that the universe must therefore have had a beginning. This infinity symbol does not conflict with any of the arguments that I explained in the previous presentation. Rather, it confirms them. This kind of infinity is not really an infinity at all. It is merely saying that something that is finite can always be made larger. Philosophers call this kind of infinity a potential infinity. A potential infinity is not even a mathematical object, let alone a quantity. It does not exist on the x-axis. It cannot be the object of any mathematical operation, and it isn't part of any mathematical system. It is, as I have emphasized several times in this presentation, an imaginary concept. It does not stand for, it does not represent any physical quantity. It is merely saying that something that has a particular size can be made larger without end. As an aside, it is in this sense that we say that the pleasures of paradise and the horrors of the hellfire are infinite. In the Quran, God tells us that the people of paradise and the permanent inhabitants of hell will remain in paradise or hell forever without end. That means that the time for which they will remain inside paradise or hell will keep on increasing without any end. There will never be a time, in other words, that will not be followed by another moment of time. But at any given moment, the total quantity of time that will have elapsed since the beginning of everything, since the time that God created everything, that quantity of time will always be finite. The fact that mathematicians use this first kind of infinity, the sideways figure 8, then, is not an argument for the fact that the universe did not begin to exist. Quite the opposite. It is actually part of an argument for the fact that the universe did begin to exist. And it describes a property of finite quantities, that they can be made larger without end, not of infinite ones, which are impossible. I have explained why the first kind of infinity does not give an atheist any grounds for objecting to the arguments of the previous presentation. Let's now turn to the second kind of infinity. Unlike the first kind of infinity, which is a potential infinity, mathematicians consider the second kind of infinity to be an actual, a completed infinity. Just the kind of infinity that I have shown cannot exist in the statement, the universe has existed for an infinite quantity of time, or the statement, an infinite quantity of time has elapsed in the universe. Mathematicians use the second kind of infinity in a discipline called the foundations of mathematics, and in order to understand why this second kind of infinity does not describe physical quantities, we need to understand what exactly the foundations of mathematics is all about. I want you to recall first that ancient mathematics used numbers that directly described physical quantities. Next, I want you to recall that modern mathematics is more abstract. Remember that algebra and the Cartesian plane extended the ancient concept of numbers to mathematical objects such as negative and complex numbers, which are more abstract than ancient numbers and don't therefore describe any physical quantity. The foundations of mathematics is a field of study that is even more abstract and far removed from the real world than modern mathematics. Remember that even though the mathematical objects of modern mathematical systems do not directly describe physical quantities, they are indispensable for scientists who make inferences about the real world. Modern mathematics, in other words, is widely used to make inferences about the real world. The goal and purpose of the foundations of mathematics is not to make any inference about the real world at all. The goal and purpose of the foundations of mathematics is to engage in a philosophical inquiry into the modern mathematics as a whole. The goal and purpose of the foundations of mathematics is to define what various kinds of mathematical objects exactly are, what various kinds of mathematical operations exactly are, what exactly the mathematical rules of various mathematical systems are, all so that we can study the kind of inferences that can be made by the mathematical system that we are studying. The foundations of mathematics is not a field of study that interests scientists. The foundations of mathematics is a field of study that interests philosophers and logicians who want to come to a very precise understanding of how mathematical systems work, and therefore ask highly abstract and theoretical questions, sometimes for practical purposes, and very often for no practical purpose at all, but for their own sake. I will therefore refer to those who study the foundations of mathematics not as mathematicians, but as philosophers of mathematics. I want you to observe that if the objects of modern mathematics, which are used to analyze the real world, if these objects do not describe physical quantities, then the objects of the foundations of mathematics, which are used by the philosophers of mathematics and not by scientists, and these philosophers, they ask questions unrelated to the real world, then the objects of the foundations of mathematics should, a fortiori, by greater right, not describe any physical quantity at all. If you like, you can stop listening to this presentation now, because you have understood why this object, this second kind of infinity, is an imaginary concept. You have understood why it does not describe any physical quantity at all. If you like, you can continue listening to this presentation so that the reason why this is the case becomes absolutely clear. Let's return to a deeper examination of this second kind of mathematical infinity and its role in the foundations of mathematics. Remember that philosophers of mathematics are interested in what exactly the mathematical objects, mathematical operations, and mathematical rules of mathematical systems are. In order to define these things exactly, they need a precise and expressive language. An important part of that language is what mathematicians call set theory. This second kind of mathematical infinity is part of the language of set theory. Set theory was invented in the late 19th century by a German philosopher of mathematics named George Cantor. Cantor built on the work of an earlier philosopher of mathematics named Richard Dedekind. Dedekind developed set theory as a creative solution to the difficult philosophical problem of defining the real numbers. The real numbers are composed of the rational numbers, which we've already learned about, plus the irrational numbers, which I will now explain. Remember that rational numbers are a combination of the natural numbers and the fractions, extended backwards into 1, 0, and the negative numbers. Rational numbers are not all of the numbers that we have. There are several important numbers that are called irrational numbers. The most famous irrational numbers are the square root of 2, Euler's number, or E, and pi. I will not show you why these numbers are irrational. If you don't already know, and if you are interested in finding out why, I will leave you to research it for yourselves. For the purposes of this presentation, you don't have to know why these numbers are irrational. You just have to know what it means for them to be irrational. What it means for these numbers to be irrational is that they cannot be expressed by any finite series of decimals. That is why the long decimal numbers that represent each of these three numbers have 3 dots at their end. No finite series of decimals can ever specify any of these numbers exactly. But you can keep on adding more and more decimals, and that will get you closer and closer to the real value of these numbers. Another way of saying this is that they cannot be expressed with ratios as we do with rational numbers. This is where the philosophical problem that Dedekind was trying to solve arises. If we cannot pinpoint the location of these numbers on the number line using ratios, then how do we pinpoint their location on the number line? Dedekind's answer was that although we cannot pinpoint the location of these numbers using a single ratio, we can pinpoint their location using an infinite number of ratios, like this. Let's take the square root of 2. The square root of 2 is here, at this point on the number line. We can pinpoint the location of this point by dividing the number line into two halves. The first half contains the collection or set of all the rational numbers that are less than the square root of 2. The second half contains the collection or set of all the rational numbers that are larger than the square root of 2. The square root of 2 is that number that divides the number line exactly into these two sets. What concerns us in this presentation is that pinpointing the square root of 2 on the number line requires both of these sets to be infinite, or in other words, unbounded in both directions. It is easy to see why each of these sets must be unbounded in the direction away from the square root of 2. For example, the first set must be unbounded to the left because in order for it to pinpoint the square root of 2, it must cover every number that is less than the square root of 2. It must therefore include all numbers to the left of that point. One way to say this is that it includes the numbers all the way to minus infinity. Now, the infinity that I am using here is the first kind of infinity, the sideways figures 8. And I have just explained that this infinity is not a point on the number line at all. No matter how far back you go, you will never reach a number called minus infinity. And you can always go even further. So if you can't say that this set includes all numbers to minus infinity, then what exactly do you say? Dedekind did not give a definitive answer to this question. It was Cantor who answered this question, and it is in his answer that the second kind of infinity that we are examining here arises. I will return in a little while to explain his answer. For now, I will let the ambiguity stand. It is easy to see that the second set on the right must be unbounded to the right for the same reason that I have just explained with the first set. I'll leave that to you. I'll leave that for you to work out for yourself. The key point here is not the unboundedness of these two sets to the left or to the right. The key point here is their unboundedness in the direction of the square root of 2. Remember that the square root of 2 is an irrational number that cannot be expressed with a finite number of decimals. The decimals keep going on and on and on. Every extra decimal brings you closer to the exact value of the square root of 2, but you never quite get there. What this means is that you can approach the square root of 2 from the left with rational numbers that have a finite number of decimals that get closer and closer to the square root of 2 from below. And you can also approach the square root of 2 from the right with rational numbers that have a finite number of decimals that get closer and closer to the square root of 2 from above. Since the square root of 2 cannot be specified by a finite number of decimals, each of these two sets is unbounded because you can keep on adding decimals such that the number on the left gets closer to the square root of 2 but is still less than it, and the number on the right also gets closer to the square root of 2 but is still greater than it. This continues without end. If you take each of these two unbounded sets as a whole, then you have divided the number line into two parts using an infinite number of rational numbers. And the point that lies exactly in the middle of this division, the point that divides the number line into two, is the square root of 2. Today, most philosophers of mathematics consider Dedekind's method to be revolutionary. In his honor, they call his method the Dedekind Cut, because it defines irrational numbers by using them to cut the number line into two halves. Dedekind's method precisely defines irrational numbers such as the square root of 2. But that definition requires the use of infinite, unbounded sets. And this is why the second kind of infinity arises. This second kind of infinity arises in the foundations of mathematics because it gives philosophers of mathematics a neat and tidy way to define irrational numbers such as the square root of 2. Now, Dedekind's method is only a neat and tidy way of defining irrational numbers if there is a clear definition of what exactly an infinite set is. Remember that saying that an infinite set is one that continues to plus or minus infinity, the first kind of infinity that is not a clear definition, because the first kind of infinity is not a point on the number line at all. If the concept of infinite sets is undefined and unclear, then Dedekind's method will not have given any clarity on the irrational numbers at all. It will only have replaced one ambiguous concept, the concept of irrational numbers, with another ambiguous concept, the concept of infinite sets. This is where Cantor comes into the picture. Cantor gave a precise mathematical definition of infinite sets and, in so doing, invented the second kind of mathematical infinity. But before I explain how Cantor defined infinite sets, I want to explain how he did not define infinite sets and why he did not define them that way. The most straightforward way to define any set or collection of elements is to construct that set by listing its elements. The set or collection of natural numbers from 1 to 5, for example, is the set that contains the elements 1, 2, 3, 4, and 5. We have constructed the set by listing its elements. Cantor did not use this method to define infinite sets. He did not construct infinite sets by listing their elements. The reason why he did not construct infinite sets by listing their elements is because he understood that this was impossible. It is impossible to construct an infinite set by listing its elements, because if you start with a set that has one element and then keep adding elements, you will never reach an infinite set, no matter how long you keep on adding elements, and no matter how many elements at a time you add. If you continued for 1,000,000 years adding 1,000,000 elements per second, you would have an unimaginably large set, but that set would still be finite and bounded, because you will always be able to add more to any quantity of elements or numbers that you have. And you can only add more to something if that something has an end, or in other words, if it is bounded and finite. This, in fact, is one of the arguments against the existence of an actual or completed infinite collection of anything. The argument is very simple. If there is an actual or completed infinite collection of anything, you must be able to construct it. But it is impossible to construct it, because no matter how long you keep on adding elements, you will never reach your goal. I must at this point digress for a moment to show you why an atheist who believes the universe has existed for an infinite quantity of time is completely irrational. The argument that I have just given is why scientists will never prove that anything in the universe is actually infinite. Science is based on human observation, and humans can only observe a finite quantity of things at a time, because the senses with which we capture those observations are finite, and the brain cells with which we store those observations are also finite. We can only observe a finite number of things at a time, and we can only think of a finite number of things at a time. No matter how long we live, the number of things that we will have observed and the number of things that we will have stored in our memories will never reach an actual or completed infinity. Now, I have explained in the 5th episode of this series that when atheists say that belief in God is like believing that a solar eclipse is caused by a dragon that is trying to eat the sun, I have explained that this is a straw man argument, because there is no evidence for the claim that the solar eclipse is caused by a dragon that is eating the sun, but there is, on the other hand, a great deal of evidence for the fact that God exists. If you have followed carefully what I have just said, and if you have also followed the arguments that I gave in the previous presentation, you will see that to claim that anything in the universe is actually infinite, or to claim that the universe has existed for an infinite quantity of time, is exactly like believing that solar eclipses are caused by a dragon that is trying to eat the sun, because there is absolutely no scientific or philosophical evidence that proves that this is true. In fact, to believe that anything in the universe is actually infinite, or to believe that the universe has existed for an infinite quantity of time, is even more preposterous. Because when the ancient Chinese believed that solar eclipses were caused by sun-eating dragons, they merely reached a conclusion based on insufficient evidence. But when today someone claims that anything in the universe is actually infinite, or that the universe has actually existed for an infinite quantity of time, they are reaching a conclusion in the face of evidence to the contrary. I have just given you an argument for why an actual or completed infinite quantity of anything is impossible, and in the previous presentation I gave you 3 other arguments as well. Atheists who hang on to the concept of an actual infinity in order to avoid the obvious conclusion from the fact that the universe began to exist, that God exists in other words, are not rational or intelligent at all. They are even less rational than the ancient Chinese who believed that solar eclipses are caused by sun-eating dragons, even less rational than the ancient Vietnamese who believed that they were caused by hungry frogs, even less rational than the ancient Hindus who believed that they were caused by the head of a decapitated god that was chasing the sun and moon to eat them up, and even less rational than the ancient shamans who believed that they were caused by hungry spirits that were trying to eat up the sun. Let me now return from this short digression to the main subject of this presentation. Cantor fully understood that it is impossible to construct an infinite set of anything by listing its elements, because it is impossible to construct an infinite collection of anything by listing its elements. Now, for some philosophers of mathematics, the fact that it is impossible to construct an infinite set in this way entails that the very concept of an infinite set is an incoherent concept. For such philosophers, there is no such thing as an infinite set, because we can never make one and show it to you. And even if we were to assume the impossible and suppose that someone did actually make an actual infinite set, we would never be able to verify that it is actually infinite, because, as I have just explained, we only have a finite number of brain cells and can therefore only actually bring to our mind things that are finite. Believing in infinite sets would then be just like believing that solar eclipses are caused by sun-eating dragons. According to these philosophers, infinite sets are just figments of our imagination. And this second kind of infinity is an incoherent concept. There is, in other words, no such thing as this second kind of infinity, and any mathematician who thinks so is simply wrong. I think that these philosophers are correct. Again, if you like, you can now stop listening to this presentation, because you have understood why this mathematical object, this second kind of infinity, is an imaginary concept that is not even coherent, let alone descriptive of any physical quantity. Or, if you like, you can keep listening so that the reason why that is the case becomes even more clear. I believe that those philosophers who think that infinite sets are figments of our imaginations are correct. This is, in fact, what most philosophers have thought for most of human history. Today, however, infinite sets are part of the mathematical mainstream, and philosophers of mathematics who believe that they are imaginary are a minor voice in the professional philosophy of mathematics. If you are hesitant to accept my conclusion merely because it goes against the mainstream voice of professional philosophers of mathematics, then I urge you to be confident in your own ability to reason, and not merely accept conclusions because other people are saying them. Remember that the mainstream academic community was wrong when Copernicus argued that the Earth goes around the Sun. It was wrong when Michelson and Morley argued that light did not need any luminiferous ether to travel in. It was wrong when Einstein argued that time is not absolute. And it has, in fact, been wrong hundreds of times during the past few centuries. The issue at hand is not complicated. It does not require a PhD in mathematics to understand. Anyone with a good high school education can see it for themselves and you can too. But in order to show you beyond any shadow of a doubt that this second kind of mathematical infinity is an imaginary concept that does not describe physical quantities, I will assume for the sake of argument that the current mainstream is correct. I will assume for the sake of argument that this second kind of mathematical infinity is not a figment of our imagination, but a mathematical object that fits coherently into modern mathematical systems. Now, the point that I want you to understand is this. I want you to understand that even if the professional mainstream is correct, even if this second kind of mathematical infinity is a coherent mathematical object, it is still an imaginary concept in the sense that it does not describe any physical quantity. And as a result, its existence in the minds of modern mathematicians is not an argument against the fact that the universe began to exist. All you need in order to see this is to reflect a little bit on what exactly modern mathematics is and what exactly it is that modern mathematicians do. When modern mathematicians define some concept, such as negative or imaginary numbers, or such as the second kind of infinity, they are not describing anything that exists, but simply imagining something in their minds. Let me explain that more clearly. Let's step away from mathematics for a moment and look at science. When scientists define something, they are describing something that exists. For example, when scientists define a human cell as the smallest structural and functional unit of an organism, typically microscopic and consisting of a cytoplasm and nucleus enclosed in a membrane, they are describing something whose existence they have observed. The concept that they are defining is not imaginary, but real. Scientists describe real things. But that is not what mathematicians are doing when they define something. When mathematicians define negative numbers, imaginary numbers, or infinite sets, they are not describing anything that exists. When they define negative numbers, imaginary numbers, or infinite sets, they are imagining certain concepts in their minds and placing those concepts in certain well-defined relations with other concepts in their minds. For example, when they define imaginary numbers, they are imagining the concept of the square root of -1 in their minds and placing it in certain relations with other non-imaginary numbers, using the mathematical operations of addition, subtraction, multiplication, division, exponentiation, and so on. And when they define infinite sets, they are imagining the concept of an infinite set in their minds and then placing them in certain relations with respect to points on the number line. That is what Dedekind did with his cut. All of these are imaginary concepts. What I mean by this is that they are things that mathematicians have imagined in their minds, not descriptions of things that they have observed to exist. When mathematicians define these concepts, they are merely imagining them, not describing anything that is real. There's nothing wrong with imaginary concepts. Imaginary concepts can be useful. Negative and imaginary numbers are imaginary concepts, and as we have seen, they are very useful. As far as imagination is concerned, all of these concepts are, according to the professional mathematical mainstream, valid and coherent concepts. I am, for the sake of argument, granting this to them with respect to infinite sets. I am granting them that the concept of an infinite set is a valid and coherent concept. But what I want you to understand is that the fact that a mathematical concept is valid and coherent does not mean that it is real. To infer from the validity and coherence of something that I have imagined in my mind that it is also real, that it exists in the real world outside of the mind, to make that inference is to commit a logical fallacy called begging the question. For example, let's imagine the concepts of a pink elephant, a white unicorn, and a purple giraffe. Now, let's place these concepts into relations with each other, like this. We'll say that a pink elephant plus a white unicorn equals a purple giraffe. we'll say that a pink elephant plus a white unicorn minus a purple giraffe equals 0. That's pretty straightforward. You just move the purple giraffe on the right-hand side of the equal sign to the left-hand side, and you change its sign. You change it from a positive to a negative number. Simple algebra. And you can say that a pink elephant equals a purple giraffe minus a white unicorn. Also simple algebraic manipulation. Now, if these relations are defined with mathematical care, and that's not something that I've taken the time to do in this example, then they will be coherent relations, meaning, for example, that any operation on any mathematical object will always produce a mathematical object that is within the mathematical system. There are other criteria for coherence that I'm omitting here because what those criteria are is not relevant to the point that I'm making. But the fact that we have imagined these concepts and established a series of mathematical relations between them does not entail that any of them are real. The fact that we have imagined and defined these concepts does not entail that there really are such things as pink elephants, white unicorns, or purple giraffes. To see whether or not any of these imagined concepts are real, it is not sufficient to simply imagine them and define a coherent set of relations. To see whether or not any of these imagined concepts are real, we need evidence that they are real. If we assume that they are real merely because we have imagined them, then we are rushing to the conclusion without evidence. We are imagining that merely imagining them proves that they are real. We are, a logician would say, begging the question by sneaking the conclusion into the premises instead of giving evidence for its truth. Now, we can legitimately imagine the concept of imaginary numbers, but we cannot legitimately infer from the fact that we have imagined them that they are real. To see whether or not imaginary numbers are real, we need evidence. We need observation and reasoning. If we look around us, we don't see imaginary numbers walking on the street. We don't see them flying in the sky. We don't see them growing out of the ground. There is no such thing as an imaginary number in the real world. An imaginary number is an imaginary concept. It is an imaginary concept that is useful, as I have just explained, but it remains an imaginary concept. To assume that it is real merely because we can imagine it begs the question. In the same way, we may be able to legitimately imagine the concept of infinite sets. And these concepts may be tremendously useful for philosophers of mathematics, but we cannot legitimately infer from the fact that we have imagined them that they are real. We cannot infer from the fact that we can imagine an infinite set that it is real, because that would be begging the question. If, for example, we infer from the fact that we can imagine an infinite set that it is possible for an infinite collection, an infinite quantity of time to elapse, that would be begging the question. Because to see whether an infinite collection of time is real, it is not enough for us to simply imagine it. We need evidence. We need observation and reasoning. That observation and reasoning is what I did just a little while ago, and that is what I did in the previous presentation. I have just shown you that it is impossible to observe an infinite quantity of anything, and in the previous presentation I gave you 3 arguments for why it is not possible for an infinite quantity of time to elapse. The fact that a mathematician or anyone else has imagined an infinite collection of time merely means that it is an imaginary concept. When we subject that imagination to the tests of observation and reasoning, we clearly see that it is not real, that it does not and cannot exist in the real world. An infinite set is an imaginary concept. An infinite set does not describe a real physical quantity of anything. When a mathematician defines a concept, he or she is imagining it, not describing anything that is real. Once again, if you like, you can now stop listening to this presentation because you have understood why this mathematical object, this second kind of infinity, is an imaginary concept that does not describe any physical quantity. Or, if you like, you can keep on listening so that the reason why that is the case becomes even more clear. I will now describe how Cantor defined infinite sets. I will show you that if you understand Cantor's definition, you will see that it is not describing any physical quantity but something completely different. Along the way, I will also give you another proof for the impossibility of any actual or completed infinity. I want you to remember that Cantor fully understood that it is impossible to define an infinite set by constructing it from its elements. That is why he did not define infinite sets by constructing them, but by using a technique that philosophers of mathematics call one-to-one correspondence. Let me explain the meaning of one-to-one correspondence by showing you how Cantor used it. Cantor observed that the set of natural numbers can be put into a one-to-one correspondence with the set of square numbers. That means that every element in the set of natural numbers can be uniquely mapped to an element in the set of square numbers like this. 0 can be mapped to 0, 0 squared. 1 can be mapped to 1, 1 squared. 2 can be mapped to 4, 2 squared. 3 can be mapped to 9, 3 squared. 4 can be mapped to 16, 4 squared, and so on, without end. Every natural number, in other words, can be mapped to the square of itself. Cantor then assumed that each of these sets is actually unbounded, that it is actually infinite. I want you to observe here that Cantor simply assumed this. He did not prove it. I will return to the significance of this shortly. Cantor thought that if his assumption is true, that each of these sets is actually infinite, then the two infinite sets will have the same size. They will have the same size because every time you pull out a natural number, you can also pull out its corresponding square. Now, if you look at these two sets from another perspective, you will see something that is very strange. The set of square numbers is, in fact, a subset of the set of natural numbers. Another way of saying this is that the set of square numbers is a part of the set of natural numbers. If you list the natural numbers, the square numbers are some of the natural numbers. As you go from one square number to the next, the number of natural numbers in between consecutive square numbers gets larger and larger. If you list the natural numbers from 0 to any number, no matter how large, the size of the set of natural numbers in that interval will always be larger than the size of the set of square numbers in that interval. So do the two sets have the same size, as Cantor saw from the perspective of their one-to-one correspondence, or is one smaller than the other, as it appears from this perspective? Hundreds of years ago, Muslim theologians saw that these conflicting perspectives are evidence for the impossibility of an actual infinite. Here is an overview of their argument. They started by taking the existence of an actually infinite collection of anything as a hypothesis to be tested, rather than an unproven assumption, as Cantor did. They tested the hypothesis by assuming its truth and then observing that the assumption of its truth leads to a contradiction. Whenever assuming the truth of a hypothesis entails a contradiction, then we know that the hypothesis is not true as originally assumed, but false. Logicians call this kind of argument a reductio ad absurdum argument, or in simple English, a proof by contradiction. Let me now explain their argument in detail. Let's assume that a certain collection, say the collection of years that has passed from now into the past, let's assume that this collection is actually infinite. This leads to a contradiction. The contradiction is that if you create a subset of this infinite collection by starting not from now, but from some time in the past, let's say the time of the American Revolution, for example, then you can plainly see that this subset is smaller than the original set because it has fewer years in it. Fewer by the number of years that have passed from the time of the American Revolution to the present moment. But on the other hand, if you look at the two sets separately and set up a one-to-one correspondence between them, then every year in the original collection can be uniquely associated with a year in its subset, without end. This entails that the two sets have the same size. But this is a contradiction. The first analysis shows that the subset is smaller than the original collection. The second analysis shows that it has the same size. And it is a contradiction for the subset to be both smaller than the original collection, or in other words, to not have the same size as the original collection, and for it to have the same size as the original collection. A simple way of saying this is that if we assume that the past is unbounded, then the everyday passage of time that we experience entails that the total amount of time that has ever elapsed is increasing. Whereas, if we set up a one-to-one correspondence between any sub-collection of previous time with the total quantity of time that has elapsed, then that entails that the total quantity of time that has elapsed is unchanging. Assuming that the collection of years into the past has no beginning, that it is unbounded, actually infinite, then leads to a contradiction. Therefore, that assumption is false. The collection of years into the past is not unbounded and infinite, but bounded and finite. Muslim theologians called this argument Burhan al-Tatbiq, which means the proof for the impossibility of an actual infinite by one-to-one correspondence. And they have cited one-to-one correspondence as evidence for the impossibility of an actual infinity of any collection for hundreds of years. Cantor, however, ignored this contradiction. Not only did he ignore it, he embraced it by making the contradiction his defining characteristic of infinite sets. He defined an infinite set as one that can be put into a one-to-one correspondence with its subset, which he interpreted to mean that the superset and the subset have the same size. Once again, you can, if you like, stop listening to this presentation because you understand that the very technique that Cantor used to define infinite sets is evidence for their impossibility, and mathematical infinities that result from those infinite sets are therefore imaginary concepts, mathematical mistakes that don't describe any physical quantity. Or, if you like, you can keep on listening so that the reason why that is the case becomes even more clear. Let's return again to an examination of how Cantor described infinite sets and what he meant by this second kind of infinity. In order to understand what Cantor meant, we need to understand at a high level three philosophical proofs that made him famous in the professional mathematical community. In his first proof, Cantor argued that it is possible to set up a one-to-one correspondence between the natural numbers, mathematicians represent the set of natural numbers with this fancy n, and the rational numbers, mathematicians represent the set of rational numbers with this fancy q. Remember that the rational numbers are a mix of the positive and negative integers and the fractions. Now, this is quite surprising. The fact that you can set up a one-to-one correspondence between these two sets is quite surprising because at first glance there seem to be many more rational numbers than natural numbers. But Cantor came up with a clever method for setting up his one-to-one correspondence. To make his method easier to understand, I will restrict myself to the positive rational numbers. Cantor carefully organized the rational numbers into a square with unbounded length and width like this. The first row of this square has all of the whole numbers, all of the rational numbers, in other words, that arise from a division by the number 1, which doesn't do anything at all to the number. The second row has all of the rational numbers that arise from a division by 2. The third row has all of the rational numbers that arise from a division by 3. The fourth has all of the rational numbers that arise from a division by 4, and so on. You can locate any rational number on the intersection of some row and column of this square. Cantor then traversed this square along its diagonals like this, labeling each location with a natural number. Now, you can arrive at any rational number if you continue for long enough along this diagonal path. And that is the same as saying that you have set up a one-to-one correspondence between the natural numbers and the rational numbers. Philosophers of mathematics call this kind of an argument a diagonalization argument. In his second philosophical proof, Cantor argued that it is impossible to set up any one-to-one correspondence between the natural numbers and the real numbers. Mathematicians represent the set of real numbers with this fancy R. Remember that there are some numbers called irrational numbers that cannot be represented by a ratio of any natural numbers. These numbers include the square root of 2, pi, and Euler's number e. Remember also that Dedekind used infinite sets to define these irrational numbers using his Dedekind cut. Now, real numbers are those numbers that combine the set of the rational numbers with the set of the irrational numbers. In this second argument, Cantor used a proof by contradiction, which I will not explain in this presentation, to show that it is impossible to set up any one-to-one correspondence between the natural numbers and the real numbers. Now, if you can set up a one-to-one correspondence between the natural numbers and the rational numbers, as Cantor showed in his first proof, but you cannot set up a one-to-one correspondence between the natural numbers and the real numbers, as he showed in his second proof, then what exactly does that mean? To Cantor, it meant that the infinite set of the natural numbers and the infinite set of the rational numbers have the same size. These vertical lines are mathematical notation for an operation on sets that defines or that gives you the size of the set. So for Cantor, it meant that the natural numbers and the rational numbers, the set of natural numbers and the set of rational numbers have the same size, but the infinite set of the real numbers, the size of the infinite set of the real numbers is larger than the size of the infinite set of the natural numbers or the infinite set of the rational numbers. Cantor called the size of the natural numbers and the rational numbers aleph naught. Aleph is over here is the first letter of the Hebrew alphabet, and he called the size of the set of real numbers aleph 1. Then he said that the size of aleph 0 is less than the size of aleph 1, which is another way of saying that the set of real numbers is larger than the set of the natural numbers, and both of these are infinite sets. The third proof that made Cantor famous is his proof that there are infinite sets that cannot be placed into a one-to-one correspondence with the set of real numbers, other infinite sets that cannot be placed into one-to-one correspondence with these sets, and so on. To Cantor, this meant that there are infinite sets that are larger than the set of real numbers. So if the size of the infinite set of the real numbers is aleph 1, as we just saw, then the size of the class of infinite sets that are larger than this is aleph 2, and the size of the class of infinite sets that is larger than that is aleph 3, and so on. Cantor considered aleph naught, aleph 1, aleph 2, aleph 3, aleph 4, and so on to be a new kind of number. Each of these numbers describes the size of a kind of infinite set. Cantor called these numbers transfinite numbers. These transfinite numbers are what Cantor meant by this second kind of mathematical infinity. Now that you understand the meaning of the second kind of mathematical infinity, I will show you that just as negative and complex numbers do not describe any physical quantity, these kinds of mathematical infinities or transfinite numbers, assuming that they are valid mathematical concepts, also do not describe any physical quantity. Let's return to the three necessary characteristics of every physical quantity that I explained at the beginning of this presentation and see whether or not they apply to these new mathematical infinities. The first necessary characteristic of every physical quantity is that it be divisible. An infinite set whose size, quote in quotes, quote unquote size, is aleph naught or any other aleph, is not divisible, because if you divide any infinite set whose quote unquote size is aleph naught into two parts, then the quote unquote size of the two subsets is also aleph naught. Remember that Cantor's definition of an infinite set is a set that can be put into a one-to-one correspondence with its subset. This means that the quote-unquote size of its subset is the same as the quote-unquote size of the superset. There is a reason why I'm putting the word size between quotes. I will explain that reason shortly. Now, you might object that the superset is indeed divisible into its two subsets, because you can break the superset into its two subsets and then put the two subsets together using what philosophers of mathematics call the union operation to form the original superset. But that is not what we mean when we say that physical quantities must be divisible. What we mean when we say that physical quantities must be divisible is that they must be physically divisible into groups of smaller physical quantities. 6 apples, for example, are physically divisible into 3 smaller physical quantities of 2 apples each. The division of an infinite superset into its 2 infinite subsets has a different meaning than the division of a finite collection into its 2 finite collections. When the concept of sets or collections of elements was extended to include infinite sets, the meaning of their division and recombination also changed. As I have already explained several times over, when the objects of mathematical operations change, the meaning of those operations also changes. These new transfinite numbers, therefore, do not describe anything that is divisible. The second necessary characteristic of every physical quantity is that it be composed of units. Aleph naught, like all of the other alephs, does not describe any physical quantity, because infinite sets that have any of these quote-unquote sizes are not in fact constituted from units. Now, I have already drawn your attention to the fact that whenever I have talked about the quote-unquote size of infinite sets, I put the word size in between quotes. I will now tell you why. The reason why I have been putting the word size in between quotes is because aleph naught, aleph 1, aleph 2, aleph anything is not really the size of anything. The size of this collection of apples is 4. The size of this collection of apples is 6. The size of any collection is the number of units from which it is composed. The number of units from which this collection of apples is composed is 2. Therefore, it has a size of 2. The number of units from which this collection of apples is composed is 4. Therefore, it has a size of 4. The number of units from which this collection of apples is composed is 6. Therefore, it has a size of 6. The number of units or years from which the total quantity of time that has ever elapsed since the beginning of the universe is about 14 billion. Therefore, the size of the quantity of time that has elapsed since the beginning of the universe is about 14 billion years. 2, 4, 6, and 14 billion are all numbers on the number line that are composed of units. Aleph naught, aleph 1, aleph 2, or aleph anything are not numbers on the number line. They are nowhere on the number line. No matter how far you go, you will never reach them, because they are not numbers at all. The reason why they are not numbers is because they describe the quote-unquote size of infinite sets. And I have already shown you that it is impossible to construct an infinite set from its units. I have already explained that Cantor fully understood that it is impossible to construct an infinite set from its units, and that is why Cantor talked about the one-to-one correspondence between infinite sets rather than the composition of infinite sets by some number of elements. Aleph naught, Aleph 1, Aleph 2, or Aleph anything are descriptions of the kinds of one-to-one correspondences that can be set up between sets. Cantor called this the size of those infinite sets, but the word size is being used in a different meaning here than when it is used to describe the size of a finite set, like this collection of apples or the collection of years that have elapsed since the beginning of the universe. The sizes of these collections are sizes of things that are composed of units. These sizes are descriptions of physical quantities. The quote-unquote size of infinite sets is not the size of anything that is constructed from units. These sizes are not the description of any physical quantity. When the object of the quote-unquote size operation changed from finite sets to infinite sets, the meaning of the size operation also changed. Aleph naught, like all of the other alephs, does not describe any physical quantity because it is not a number that is composed of units. It is nowhere on the number line. It is, as the title of this presentation says, an imaginary concept. The third necessary characteristic of every physical quantity is that it must be describable as being equal to, greater than, or less than some other physical quantity. Aleph naught, Aleph 1, Aleph 2, and all of the other alephs do not describe any physical quantity because they are not describable as being equal to, greater than, or less than any other physical quantity. Now, you might object that Cantor defined each aleph as having the same size as other alephs of the same degree. He defined alephs of a larger degree as being greater than the alephs of a smaller degree, and he defined the alephs of a smaller degree as being less than alephs of a larger degree. But that is not what we mean when we say that physical quantities are describable as being equal to, greater than, or less than other physical quantities. I have just explained that Aleph naught, Aleph 1, Aleph 2, Aleph anything are not numbers that are found anywhere on the number line. They do not describe the physical size of anything. They are even more different from the natural numbers than negative numbers or imaginary numbers are. The equal to, greater than, and less than operations do not have the same meaning when applied to transfinite numbers and infinite sets that they do when applied to normal numbers. Just as the meaning of the mathematical operations of equality, greater than, and less than changed when we moved from natural numbers to negative and complex numbers, their meaning changed even more when we introduced infinite sets. These kinds of mathematical infinities, transfinite numbers, then, do not describe any physical quantity because none of the three necessary characteristics of physical quantities apply to them. These kinds of mathematical infinities are, as the title of this presentation says, imaginary concepts. I have given you 5 reasons why this second kind of mathematical infinity is an imaginary concept that does not describe any physical quantity. First, I showed you that this second kind of mathematical infinity is an object that is not used by mathematicians, but by philosophers of mathematics in a field of study called the foundations of mathematics. Unlike mathematics proper, which is used by scientists to study the real world, the foundations of mathematics is something that is used by philosophers to study the meaning and coherence of mathematical objects, operations, and rules of mathematical systems. This second kind of mathematical infinity is therefore even less descriptive of physical quantities than mathematical objects such as negative and complex numbers are, which we have already learned do not describe physical quantities. Then I showed you why it is impossible to construct an actually infinite collection of anything. I used the argument that I showed you here to show you why believing in the existence of an actual infinite collection of anything is like believing that solar eclipses are caused by sun-eating dragons. Then I used the argument to show you why the concept of an infinite set is, according to many philosophers of mathematics, an incoherent concept, a mathematical mistake. Then I showed you that even if we grant that infinite sets are coherent mathematical concepts, they still would not describe physical quantities. I explained that when modern mathematicians define any mathematical concept, they are not describing something that exists in the real world, but only imagining a concept in their minds. I explained that it is invalid to infer from the fact that someone has merely imagined something that what they have imagined actually exists in the world. It does not follow from the fact that modern mathematicians have imagined a mathematical infinity, that mathematical infinity actually exists in the real world. That kind of inference begs the question. Then I showed you that Cantor's analysis of infinite sets is based on something called one-to-one correspondence. I explained that the idea of one-to-one correspondence between infinite collections is an old concept, and that Muslim theologians used this idea as part of an argument for why an infinite collection of anything is impossible. Their argument reveals flaws in Cantor's reasoning and strengthens the position of those modern philosophers of mathematics who believe that the concept of infinite sets is an incoherent concept. Finally, I explained what this second kind of mathematical infinity actually means by showing you 3 philosophical proofs that made Cantor famous in the mathematical community. I then used this explanation to show you that this second kind of infinity does not describe any physical quantity, because the thing that it describes does not possess any of the 3 characteristics that are necessary for something to be a physical quantity. The conclusion of this presentation is clear and simple. Not only can we scientifically prove that the universe began to exist, we can also prove it philosophically without any recourse to modern science. The fact that the universe began to exist is simple and straightforward, and there are many, many clear arguments for it. I explained some of those arguments in the previous presentation and showed you some more in this one. This presentation is the longest presentation in this series of presentations on why Islam is true. The reason for its length is not because the conclusion is difficult to prove, but because the strongest objection to this conclusion in our times spreads confusion using complicated concepts. I took the time in this presentation to explain those concepts in terms that anyone with a good high school education can understand. I then showed you that if you understand the field of study in which these concepts arise, why these concepts are used, and what they mean, then you can clearly see that they are completely unrelated to the conclusion that the universe began to exist. What's more, understanding these concepts reveals even more arguments for the conclusion that the universe began to exist. وصلى الله على سيدنا محمد وعلى آله وصحبه وسلم والله سبحانه وتعالى أعلم وهو حسبنا ونعم الوكيل.